Welcome back, everyone, to the eCoreAcademy e-learning platform. Today, my name is AJay Raj, back with yet another geometry video for you all. And today's lesson topic is all about parallelograms, and this is our part 2 video, continuing off of our part 1 of parallelograms. We know that parallelograms are very important geometry, so that's why I've broken down this entire lesson into 2 separate cohesive lessons that kind of combine together, and they're supposed to be watched in their sequential order from part 1 to part 2. So a lot of the basic fundamental information in part 1 will be needed for part 2. So I suggest that you watch that one before watching this video. I'll link that in the description down below so that you can access it right here, right now. But before we jump into the meat of today's lesson, please make sure to smash that subscribe button, hit that like button on this video, as well as turning on post notifications so you don't miss out on any of our latest uploads at eCoreAcademy. Feel free to utilize the comment section down below. We really like to hear all of your thoughts and your constructive feedback, so feel free to utilize that section, and we'll try and apply any of your constructive feedback in our videos to come. So the whole point of today's lesson is to take a look at the more complex properties and proofs of parallelograms. So we started off by defining parallelograms, looking at their basic definition, how they correlate, what are some specific fundamental properties of theirs, and how do they correlate amongst quadrilaterals and T-charts in our previous video, part 1 of parallelograms. Now we're going to start to up the ante, and now we're going to look at theorems, different situations and correlations with those other quadrilaterals, some proofs in our T-charts, and formal and informal proof as well. So without further ado, let's jump right into it. First off, let's take a look at diagonal relationships. I started off the video previously with a little bit of a cliffhanger on diagonals of a parallelogram. So today we're going to look at specifically what exactly those parallelogram diagonals are and what are some unique relationships, and as well as their theorems and formal forms of proof in a T-chart, or you could also call it a 2-column chart. So the diagonals of a parallelogram. So by definition, the diagonals of a parallelogram, alike with many other quadrilaterals, are line segments that connect the opposite vertices of a parallelogram that bisect each other and form congruent angle pairs. And this is the same property developed by vertical angles, which is used as formal proof. So that's its form of proof, the vertical angles theorem. So I'm going to show you what exactly I mean. So as you can take a look here, we're going to define these lines, these diagonals, by points. We have our first point D here and our second point B here. So that means that this diagonal formed is connecting these opposite vertices that are directly opposite from each other and on a diagonal slant. Therefore, it's called a diagonal line of a given figure. In this case, the diagonal of this parallelogram, ABCD. So this diagonal will be called DB. So that's our first diagonal. And then, of course, we have our diagonal AC. Now, what are some things that we know about diagonals? Well, like I said in my definition here, diagonals bisect each other, meaning that they split each other in half. Let me highlight that a bit. I just want to highlight upon that. So bisect each other. So what is that? What exactly does this mean? If you recall to our previous basic geometric terms and our basic definitions, we know that means that it splits it along the center. It splits, each diagonal splits each other in half. So that means that DB is going to be split into DE and EB. So those are our new lines formed. So it's going to be DE and EB, and E is merely that intersection point. So it's going to bisect it into equivalent terms. And we also know that DE is going to be congruent to EB because of this bisection. That's the definition of a bisector and a midpoint when it comes to your formal proof in a 2-column chart. Or, yeah, your 2-column proof. And then AC is going to be split into AE and EC. So let's write that. AE and EC. So that means that AE is going to be congruent to, our EC line. They're same in length. And also another property that we know is that they form congruent angle pairs. Now, if we take a look at both of these intersecting lines, they're basically your intersecting line properties. So we can see that DB and AC intersect at a common point, and when they do so, what they're doing is they're intersecting and forming 4 different angles. When they form those 4 different angles, we can develop these theorems to develop which angles are congruent and how to actually shorten the process to discover what the remaining missing angle measures are. So we take a look at this angle right here, this opening angle of AB. We know that angle AB is going to be congruent to angle DEC. So we know that angle AEB is going to be congruent to angle DEC. So let's write that. So angle AEB is going to be congruent. So we'll write here congruent to our angle DEC. And this is because of the vertical angles relationship. This should be a review of something that we did way back when at the beginning of this geometry course, something that you should have learned at the beginning of any geometry course. That is the fact that our vertical angles, which are angles from intersecting lines that are opposite sides of each other, are always going to be congruent in this fact. So what can we infer based off of that? We can infer that angles ADC and also CEB are going to be congruent as well. So I'll draw those two lines here to show that they are congruent. So these two angles are going to be congruent, and these guys are going to be congruent as well. So we'll write that here. So that's AED. So angle AED. Almost started to write a line there. Angle AED is going to be congruent to angle BEC. All right, so that's our basic diagonals of a parallelogram. Let's move on to the next slide. This slide is all about calculating altitudes. Now, we know that altitudes are very important with parallelograms, and we started by looking at basic problems in which the altitude was already given to us, and we would calculate the area. That's why altitudes are very important, to calculate that area. And if we recall, parallelograms have the area formula of base times height. The base is a side length that we're already given. That's something that's easily discovered on a graph. But now we're going to start to look at altitudes and how we can calculate them when they're not given to us and when they're put on a graph. So this is all about finding distance. When a parallelogram is placed on a graph, you can calculate the unit distance within the parallelogram to find its altitude. Now, on any parallelogram, the case is that you're going to at least have one altitude on the interior of the parallelogram. And in traditional geometry, we do not focus on any possible altitude that's on the exterior. We like to focus on the interior. So we're going to try and calculate these altitudes on the interior by merely using the distance formula or by calculating your vertical unit change. So if we're taking a look at this parallelogram here, we know that this is placed on an XY coordinate plane with our X running horizontally and our Y running up vertically, and they're intersecting to form that plane. This parallelogram is located at multiple points. Here it's located at the origin, 0, 0, right here. And then as specified here, it's going to be at 7, 5. These are all the vertices that are located at these points. So this is 7, 5, 16, 5, and 9, 0. Now we're tasked with the fact of the matter that we have to find the area of this parallelogram. Now we have to calculate the base and the height. So the base is fairly easy to calculate in this situation. We know that the axis runs from 0 to 9 in terms of the vertices. So what we're going to do is we're going to subtract those values, 9 minus 0, and we get that this side, this bottom unit, is going to be worth 9 units. That's our base done. Now we have to calculate this vertical base, this vertical altitude that's going to intersect this given base here. So what we're going to do first is we're going to take a look at this point here. We know that it's 7, 5. Now what we want to do is we want to pay attention to the y-axis in this at this point, because what we're trying to do is we're trying to find that vertical distance that this altitude runs. So we're not worried about the x-axis because it's horizontal distance. So with the vertical distance of 5, what we're going to do is we're going to try and calculate where the lowest point of this altitude will be. In terms of the y-axis, we're going to ignore the x-axis because it's vertical distance. And as we can see here, it's going to intersect this given base here at a y that equals 0. So when we calculate that, we see that it's going from 5 to 0. So we subtract 5 minus 0, and we get that our altitude is 5 units. Now, don't worry, you might be thinking, well, what if our parallelogram is on a slant and it's not necessarily pointed in a direction in which you can just calculate smooth vertical or horizontal or vertical distance? What if you have to calculate diagonal distance? What if it's on a tilt, like a 90-degree or a 45-degree rotation? Well, don't worry, I'll get into that in our next video just as a little incentive, our extended problems with parallelograms. But I'm just going to put up that equation here for distance formula. So this is the distance formula. That's d equals square root of x1 minus x2 squared plus y1 minus y2 squared. And this has to do with the 2 points that you're trying to find the distance between. And in this case, it would be that top vertex, that opposite vertex to the opposite base, what exact point you want it to be on and located. So I'll get into that in our next video on extended problems with parallelograms. A little bit more complicated. That's why we're trying to separate it. So moving on to the next slide. This slide is all about exterior angles of parallelograms and how we're going to calculate them. So exterior angles of a parallelogram are direct opposites of the interior angles. So one way that we can calculate it is, if we take a look at parallelograms, we know that if you're going to have a straight angle, a straight line that goes across, we know that a straight angle is going to be equivalent to 180 degrees. Now what happens is, when we have those side lengths, those slanting side lengths, intersecting those top and bottom bases, what happens is you're basically intersecting that angle. And when you know what one angle is, whether or not it's your exterior or interior, in this case, if we know what our interior angle is, we're just going to subtract that value from 180 to find what our exterior angle is. So these angles are represented by the same side exterior angles, which are also supplementary. And this would be your form of proof when you're trying to prove that exterior angles are also supplementary and they're opposite from your interior angles. Think about it as a transversal in this case. So if we take a look at side AD, and what we're basically going to do is we're going to extend sides DC and AB just to get a hold of the angle. We have this interior angle right here. I'm going to highlight upon these. So I'm just going to make that really thick. Very thick. So we know the properties of interior angles. We know interior angles are going to be supplementary. These consecutive interior angles are going to be supplementary. We know that opposite angles are going to be congruent. So angle D and angle B are going to be congruent as A and C, and then DA are examples of our consecutive angles that are going to add up to 180 degrees. Now what we're going to try and do is we're going to try and calculate for our exterior angles as shown here. Now you might be thinking, wait, isn't an exterior angle the entire angle that goes around like this? Well, yes, it is in that case, but for now what we're going to do is we're only going to focus on this exterior angle here with this transversal, and later on we can add 180 degrees to that value, because we know that this part right here, this missing part right here, is automatically going to be equal to 180 degrees. So all we need to find is this value right here, these given values. And then we can add those values to 180 degrees. So let's start calculating that. What exactly would that be? So we know that these values D and A are also going to be supplementary values in this case, because they're going to be your same side exterior angles, but they're going to be the direct opposite of your interior angles. So if we were given that this angle right here is going to be 80 degrees, and we're given that this angle by chance is going to be equivalent to 40 degrees. Now what would happen here? What would happen here? This is in case that we're just focusing on this transversal. I know this does not work for the entirety of the parallelogram, but we're just focusing on this on these two parallel lines as if they were transversals. Now, what would this angle measure be here? So we know that it's going to be 180 minus 80. So this angle right here is going to be 100 degrees. And then what's going to happen here? So we know that this is 40 degrees, but we know that these angle measures have to be supplementary. So we can automatically change this 40-degree angle measure to discover that this side has to be 100 degrees. And we know that this angle measure here has to be 80 degrees because it has to add with 180 with 100 to get 180 degrees as shown. So that's how we calculate our measures there. And what we can do is we can add that to our 180-degree external angles that are on the opposite side to get our grand total for our external or our exterior angles to be 280 degrees and 260 degrees. Right here. All right, moving on to the next slide. This is congruent triangles. This is a very interesting slide, another theorem that I developed for you all. And this is deriving congruent triangles from parallelograms. A parallelogram can be split into two congruent triangles and a rectangle through analytical geometry. We know that from our complex figures. Some complex figures are just too complex that they don't necessarily have a given base or height specified, or we don't have a given area formula to calculate them. A parallelogram is not that case, but what we can do here is, if we're not given enough information, we can split it up into given shapes. And the most popular way to do that is splitting it up into two congruent triangles and one rectangle, or a type or a square, which is a type of rectangle, depending on the type of parallelogram. So this can prove the theorem in which opposite sides of parallelograms are congruent. What does that mean? So if we can split let's take a look at our parallelogram here. So what's going to happen here is, what if I split down right here from AB, from these points AB, what if I split this down right here, right down here? A is making that altitude again. What if I make that altitude? What do we have here? I'm going to name this point E here. Or yeah, let's name this point E. So I've just created a triangle ABE. Now I'm going to do the same thing here. I'm going to draw a straight line down to point C, or vertex C. Now what have I created here? I've created another triangle, and we'll name this point F. So I've created triangle ABE and CDF. Now what do we know about these two triangles? These two triangles are actually going to be congruent. So let's name them. ABE is going to be congruent to our CDF, triangle CDF, as shown with our congruence postulate. And what else do we have developed here? Now we have one rectangle in the very center, which is our rectangle here. I'll name that. Which is our rectangle here, and that's going to be AECF. So that's going to be rectangle AECF. And there is a very unique relationship between ABE, FDC combined together in relationship to the rectangle. So I want you guys to leave in the comments below, or hold that thought. What is that relationship? And save it for next video. I'll explain it in our extended problems on parallelograms video. So what's the relationship between AECF, our rectangle here, and our two congruent triangles, which are ABE and CDF? Just a little cliffhanger for our next video. And finally, we have our congruent trapezoids when it comes to our theorems. And I'll do one last slide upon accumulating and summarizing all of these items and putting it into formal proof. So this is a congruent trapezoids theorem. Nothing too special here. It's just another theorem with that splitting and analytical geometry in which you split up or add together two minor figures to develop a complex figure. In this case, it's your parallelogram. So a pair of congruent trapezoids can form that of a parallelogram with a combined area that is twice as large. So this is why trapezoids have bases that are averaged out to calculate their area. So what we can do is, as you can see here, this is a right. This can be considered as an isosceles trapezoid, as shown. Sorry, not an isosceles trapezoid, but this can be considered as your regular trapezoid here, as a trapezoid. And what we're going to do is we're going to try and attach another congruent trapezoid across. So right here, as you can see, all I'm doing is redrawing this given trapezoid, but I'm putting it in an upside down fashion in which it connects to this trapezoid. Now, excuse my drawing a little bit, but I hope that you guys can get the point here. What's happening here is these two trapezoids are basically forming to connect our parallelogram here. So this is developing a parallelogram. So all we're doing is switching this right here, and we're connecting it right here with, let me add a little bit of a slant. Just to show that slant right there. So what I've done here is I've taken this parallelogram, this trapezoid, flipped it around and reattached it to this trapezoid to create one giant parallelogram. If you can see here, this is one entire figure is a parallelogram, and this parallelogram is going to have twice the area of each individual trapezoid. Now on our final slide, we're going to have parallelogram proofs, and this is statements and proofs. So these are all the different statements that we're going to utilize as proofs throughout for all of our given slides here, and I'm going to tell you each one exactly what they are. So for our exterior angle slide, we know that our proof is going to be our vertical angles theorem. Or sorry, no, that's our that's the diagonal angles. I apologize. But for exterior angles, it's going to be the same side exterior angles. That's the form of proof. same side exterior angles. And remember, that means that these two angles are going to be supplementary to each other. So that's how you can calculate your exterior angles. And through the form of a transversal and two parallel lines being formed, as I showed you, extending both of the sides. Consecutive angles is formed by the theory of same side interior angles. These are your interior angles opposite from those exterior angles. Same side interior angles. We could cover this in the last video, so this is just a little recap. So same side interior angles. Then for opposite angles, we know that they're going to have a constant relationship, and that's just a property of parallelograms. So this is going to be definition of parallelograms. So definition of parallelogram. Then we're going to have parallel and congruence. That's also going to be the very same thing because that's also another property of parallelograms, just automatically given. That's definition. All right, def of a parallelogram. Just to abbreviate and save your time. And finally, for our diagonal angles, we know that the relationship opposite angles are going to be congruent, and intersecting lines, that's going to be our vertical angles. And I suggest that you at least copy that down or maybe take a screenshot of this diagram. I really like this diagram. It breaks down all of those congruence relationships amongst side lengths, angles, and the diagonals and their angles as well. All right, everyone. So that'll be it for today's video. This has been the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. Hit that post notification bell. And also feel free to utilize that comment section down below, as I said at the beginning of the video. Also, feel free to check out our website at www.ecoreacademy.org, where we have full unlocked access to what we as an online e-learning platform actually offer to you, the customers, and the public. There we have full unlocked access to note sheets, quizzes, and worksheets that go along with each and every single one of our videos, organized into separate course studies just for you. All you have to do is make an account for free. Feel free to email us at eCoreAcademy@gmail.com if you have any questions or if you just want to reach out to us. And then again, that'll be accessible on our website as well as down in the description box below. And finally, check out our social media accounts at Facebook, Twitter, and Instagram. Also, full link is in the description below, where you can check out all of our interesting content that we have there as well, aside from our YouTube and our website. And you can also utilize those mediums to share all of our videos. Once again, everyone, I hope you guys enjoyed this video. I had a blast making it. This has been AJ, and I will see you guys in the next one. Peace.